Yeah, you're probably not going to do the evil things to them that I would.
I don't think we can get away with.
I don't think we have the
Yeah.
right to do anything.
Yeah, there's that.
I've been trying for 10/10 since I like had an option and they won't give it to me.
Really?
Okay,
It's great.
okay, any questions from last time? And I did. So this is where I think that I left it. By the way, if you've been looking at the homework, I've made some progress. And so by the time I get only one homework behind, I'll assign you something else. So. 437. The domain R is a G domain. Let me see, domain the other direction. The domain R is a G domain if and only if there exists an ideal. Well, maximal ideal. And satisfies M intercept R. Zero. Right, and so we went through an example last time, and I showed you why, at least I think this is a little bit unusual, right? Because we kind of built this strange, we took a valuation domain and showed an ideal polynomial that was range was maximal, but contracted to zero. Right, so this is kind of the hallmark, or one way to think of a G domain. And this is, if you notice, we've got this characterized in terms of polynomials. So this is where we're starting to make our move to polynomials and Milstein size. So prove R be a G domain, and let K, which is the quotient field of R, be R joined with U inverse. So we can map Rx to K via call it P of X equals P of U inverse. And let me point out that, of course, this, notice that the target is what I claim it is. That is, if you have a polynomial with coefficients in R and you plug in U inverse, and that's certainly an element of quotient field. So my target's okay. And certainly this is onto, right? Because of this fact right here. Because really what the image of this certainly contains R, because it's 1-to-1 when you restrict it to R. And X goes to U inverse, and once you've got all of R and U inverse, you've got all of K, so it's on to. The image of B is all of K, so the kernel of B is M, and M must be maximum. And this is just the first isomorphism theorem, because the domain mod kernel should be isomorphic to the image, and the image is a field, so it has to be a maximal ideal. Also, since B restricted to R is the identity, let me say this. Right, I mean, just the way this map works, if you restrict to the polynomials 0 degree, then it's just the identity map. Then it must be the case that then it must be the case that M intersect R is zero. And the reason is, of course, that if M intersect R is not zero, if there's something that's in the kernel and in R, then that contradicts the fact that this subscription is 1-to-1. Right. Note that this is -1, yeah. Or +1, doesn't really matter, but anyway, notice that this has some similarities to that example that I did with evaluation domain. Remember, you remember, I think I had Q power X and the polynomial variable was T, and we had like an XT -1 or +1 in there somewhere. Okay, on the other hand, so we've shown that if R is a G domain, then we have a maximal ideal in the polynomial ring that satisfies this. On the other hand, let's go the other direction. Suppose that M is maximal and its intersection with R is 0. So it has 0 intersection with R, so it's got no constants in it. Consider the homomorphism. Say pi goes to Rx, from Rx. And this is the standard homomorphism that you would think. So pi of P of X equals P of X plus M, so it just goes to the corresponding coset. I am going to so here's a notation. So basically Z here is an element of this here, and it is the image of X from Rx. Note notice that if you think of this abstractly, this element Z, you're adjoining R, you're adjoining Z to R, you actually get a field. And hence is a determinant. So by a previous result, R is. And there we go. So what we have here is this is kind of an important characterization. Being a G domain means that you have a maximal, means that you have a maximal ideal of a polynomial ring that intersects in 0 with the coefficient. Okay. Definition. So this is for fun. Like a little party game here. Let me see if you can guess this. What are a community ring with 1 and P and R and prime ideal? we say the prime ideal P is a G ideal. If, anybody want to guess? Would this be a G ideal? Yeah, this is just fine. I don't know if there's anything. Yes, this. The key is this is prime. So R mod P is going to be a domain. So this sort of, so the idea behind the G ideal is it allows us to sort of expand the scope of what we're looking at, right? Because you might have a domain R that's not a G domain, but it might be the case that R mod P is a G domain. And if that's the case, then the thing you might outline, the prime ideal, we call it G ideal. Let me point out something sort of independent interest when it comes to G ideals. So recall first that the radical of I is equal to the radical of any ideal I is the intersection of all primes that contain it. This G ideal business allows us to sharpen this a little bit. So let's give another perspective here. So let me give you a special case of this. Zero is, in a certain sense, from this perspective, my favorite ideal, because zero is contained in every ideal. So if I look at the radical of zero, this should be the intersection of all primes that contain zero, which is, of course, the intersection of all primes. And the radical of zero is also the nil radical of R. That is the collection of everything that's nilpotent. Remember, in a community of identity, this is actually the collection of all nilpotents is, in fact, an ideal. So we can shorten this 439. The nil radical is actually the intersection of all G ideals of R. I can shorten my list, right? Instead of intersecting all the primes, I can restrict myself to only primes that are in fact G ideals, right? Notice that, of course, this contains this collection of G ideals certainly contains all the maximal ideals, right? Because the maximal ideal, R mod maximal ideal of the field, which is automatically a G domain. Right? So this is the intersection of maximal ideals and some others, perhaps others, right? Let me point out that, for example, in the integers, then the G ideals, well, what are your primes? Your primes are zero and all the ideals generated by positive primes. Zero is not a G ideal because Z mod zero, which is Z, is not a G domain, but all the maximals work. So in fact, in the integers, that's the intersection of all the maximal ideals, right? So all the non-zero primes. And notice that for the integers, the nil radical and the Jacobson radical actually coincide. So, certainly, notice that NR equals radical zero is the intersection E. E prime. Which is contained at the intersection Q, yeah. Right, so as it's usual, these kind of things that is easy, so. This containment, no radical is contained, so that's no problem. What about the other direction? Suppose that U is not nilpotent. So, and we want to show that there is a G ideal that does not contain U. So, need to show that there exists a G ideal that does not contain. To this end, since U is not nilpotent, U intersect the collection of powers N of the power U, that is. This is zero, so the ideal zero misses this, and so we can expand zero to a prime that excludes the powers of U. A prime ideal maximal with respect to the property that P intersect the set of powers. It's amazing how many times we use this over and over. There it was again. I claim P is a G. Of course, let me make sure that I point out that of course P is prime, so I've got that covered, right? Because it's maximal with respect to that property, so it's a prime. So consider R mod D, and look at the image of U. U bar, the image of U in R mod. Note that in R mod D, every prime ideal well, what can you say about every prime ideal? Correct. I'm gonna break it down a little bit more than that. Is a form Q might be where Q and R is prime and but by maximality of P. Q contains a power Q. And hence U itself. Because P was maximum with respect to not containing the power of U, so anything bigger, particularly Q, must contain the power of U. But now I know Q's prime, so it has to contain U itself. Yes.
What about the case where P equals Q? When we have to deal with that, say like P, if there's no proper prime.
Well, if there is no proper prime containing P, then that's a field. And
Right,
that's a
okay.
G.
But
So each prime mod B inside form mod B contains, and there you have it. So that means that R mod B is G domain. Either R mod B is already built itself, or when you take R mod B and you join the inverse U bar, then you'll get the quotient field R mod. I will let you work. I bet you can smell this one coming, but I'm gonna write it down anyway. And I will leave this one as an exercise. This is kind of, I think, sort of a semi-obvious next step. But R be commuted one and I and R an ideal, then the radical of I is the radical of I. So this generalizes the radical of 0. Radical of I is just the intersection of the G ideals containing I. How would you prove this? Well, the technique here, I think, is what you would think. You've already got this in the special case that I have a 0 ideal, right? So take this whole, I use this kind of sloppy terminology, but I will anyway, take this whole problem and mod out I, right? And pass to the quotient. The correspondence theorems give you what you want. Okay, any questions on that? Right. Okay, so proposition. An ideal I and R is what? This gives a different perspective. An ideal I and R is a D ideal if and only it is the contraction of a Maxwell ideal in Rx. And I'll make this, I'll clarify this. I is contraction. So that is to say, what do I mean by the contraction I mean that I is equal to this max Y deal and Rx intersected down below. Okay, so this is a good way. I mean, this gives a way of sort of building random GI deals in R, right? I mean, just find maximal ideals in the polynomial ring, just contracting them down to R. And it makes that sound even, and you get these little maximal ideals, or these little GI deals here. And it's interesting that this is the kind of the only way to do it. So, proof. If there is a maximal ideal, let's say M in Rx, such that M intersect R equal to I, then let's be careful about the details here. Then I is prime. Why is I prime? Well, because M is maximal. And I think I showed you all before that if you have any prime ideal and you intersect it down to a smaller ring, it remains prime, right? So the maximal ideal script M that we have in the first place, when you intersect it down here, it retains its prime status, at least down there. Maybe not maximal, but it retains its prime status. Hence, if you look at Ri, this is a domain. And so is its polynomial ring, because domain polynomial ring is still a domain. Claim that this is a G domain. And once we make that claim, then we'll be good to go. Almost. To see if this is a G domain, consider consider the maximal ideal M mod IX notice this ring here, this domain here is actually isomorphic to this. This is one of our fundamental kind of polynomial isomorphism identities. Consider this maximal ideal, M. Notice that M contains I by the fact it contracts down there. And so when you lift I up into Rx, then, right, you get Ix, then M certainly contains its Ix. So that makes sense here. And note that if you look at M mod Ix, intersect this is equal to 0. And this goes back to which result was it? Well, I was trying to refer back to the thing here. I'm sorry, so what was the question?
Wouldn't that just be intersect the coefficients, the R mod I? Since
let's see here.
It's not common,
Right.
You're saying
It's your
but there.
sort of river coalition.
Oh, I see.
Well, so,
Definition.
right, so I'm still confused on where we're confused here. So what's the question?
So your intersection you're taking there, wouldn't you want to take the intersection M mod IX with just R mod I?
Oh, I didn't see that. Yeah, this is part of our- Let me see, where are we at here? M intersect R is I, so we've got this thing here. This is a maximal ideal. And you intersect that with base frame. See, and what am I referring to here? Yes, you're absolutely right. Yeah, so this refers back to, this refers back to theorem 437. So, yes. This is, so I meant to say this. And so that gives me what I want in that direction. On the other hand, let's suppose that I is a G ideal, and we've got to show that it's a contraction of something from, I'm sorry, maximal ideal, mod X. So now suppose I is, yeah, I know it. Suppose I and R is a G ideal. So collect this up. So I is prime and R mod I is a G domain. So in the polynomial domain, R mod IX, there's a maximal ideal. And it is necessarily the form. Let's say, script M, mod IX. Where M is a maximal ideal of R of X. Such that M mod IX intersect R mod I 0. So we're gonna write that. Notice that this maximal ideal M must necessarily be contained in the ideal I comma X. Remember, Not all. Not all maximal ideals have that core nominal range, but this maximal under the conditions actually must be contained in I, comma, X. And since this is M is maximal and I is proper, this must be an equality. And if it's an equality, this forces M, or I'm sorry. So I inside of R is maximum. Because if you have Rx mod Ix, this is isomorphic to R mod I. And so if this is maximal in the first place, this forces I to be a maximal ideal of M, right? Because that has to be a field. And so where are we? So now what we have is I is maximal. Right, and of course. And there you go. So we get this statement that we're going right here. Okay, any questions on that?
So if I is a G ideal, then it's necessarily maximum?
An ideal. So. Yeah, does it have to be? Well, let's see, it has to be prime, that's for sure. So can it be a? No, not necessarily, because at least I'll give you an example. So for example, let's see if we can go one. Right, that's a G domain. So consider R equals notice the T is certainly primed, and when you mod out, you get this thing, T domain, right? So I see where the inspiration from this comes from. What were we doing in this proof here? Right, so I is the G ideal, and then I. So, right, here's what the thing is. I mean, the contraction of a maximal ideal doesn't necessarily have to be maximal itself, right? So let's go to the proof here. This is a G ideal, so it's prime, the quotient's G domain. So there's necessarily a maximal ideal of this thing, this quotient. It's necessarily of this form. Right, because notice as we're building this maximal ideal here, right? This M, which is a maximal ideal that actually contains this in the quotient. I think that's where the confusion might be coming from, because we built, the fact that this is a GI deal, so basically what we're doing is we're modding out by here. We built this M, but this M is actually something that already contains IX, right? And so that's why you can have, so the proof itself actually builds this over the top of IX, right? And so,
Didn't we conclude right there that I is maximal?
well, let's go through the rest of it, and make sure. So M mod IX is this, M is a maximal ideal in RX. So M is, so M mod RX, so basically, whatever this ideal here is, it contains no constant terms. So M certainly contains out, so all we need to do is argue that M contains X. Right, I guess that can be done by induction. Contains IX. And M is minus one, IX proper. So this fall here, right, that has to be true. Right, now is the ideal. So it looks like there's probably some proof here, right? Because this example right here, so let's see if we can figure out what's wrong, right? Would everybody agree that this example works, right? This is a G domain. Here's a polynomial ring, R over this. If you take the ideal generated by T minus G domain, so this is G ideal, right? But this is certainly not maximal because T is contained in X, which is maximal. Right? So what happens if we follow this through with the ideal T from here? We'll see what happens. This is G ideal. This is prime, so R mod I is G domain. Okay, well, so if you look in this ring at RY mod IY, then there exists a maximal ideal. So M is an ideal X maximal. Okay, so let's check this out. So if you have M mod IX here, M is maximal. Yeah, so a maximal ideal of this necessarily has this form. So if you look at this should be zero here. So let's see if we can make this jump here. Why is it the case that if this intersection right here is zero? Of course, we're given this, we have this condition from 4 through 7, right? So why is it then that M must be contained in X? Well, certainly M contains right, because we built it that way, right? And so to get the other containment, we really need, to get this containment, we need to verify X is in M.
So that containment should be flipped. IX is contained in M, not M is contained in I.
Well, so to get this containment, all we really need is to show that X is in M.
To
Right?
show the other.
Well, okay, so let's see. Oh, yeah, so if you get X's, right, if you get X's in M, right, then, yeah, you're right, so maybe I fit the containment here. So we know that I comma X is contained in M if we get this condition here. Now, what this means is, this means that all sort of R mod I polynomials here contain no constants, right? So this ideal here, which is a maximal ideal of this intersect coefficient ring, R mod I is 0. So there's no constant terms in this ideal. So does that mean it contains X? Well, maybe not. So it looks to me like, I need to look this over. I need to fix this proof. I must have messed this up somewhere. So what we'll do is we'll just kind of, yeah, so that's a good catch because it is certainly true that we've seen the example that I doesn't have to be maximal, so there's a slip somewhere. I'll fix that for next time. Let me give you one more theorem here for the road, and next time we'll do that one direction of 4 through 11. So let M be a maximal ideal of Rx. Suppose you have a maximal ideal of Rx, and suppose that M intersect R. Suppose when you intersect this down to the coefficient ring, of course, we've seen that this doesn't have to happen, but let's suppose that you have a maximal ideal of Rx for which this does happen. Then M can be generated by N and one more element of Rx. Then M can be generated by the stuff in N, so that is just a step down coefficient ring plus one more generator. And not only that, F can be chosen mnemonic and such that F bar I don't know what that. And such that F is an irreducible polynomial. Mod N. Irreducible over. So here's the deal. If you have a maximal ideal and you're so lucky that that maximal ideal contracts to a maximal ideal down in R, then that maximal ideal can be generated by the smaller maximal ideal in R plus one other element. And not only that, that one other element can, the other element is going to be a polynomial, right? And you can choose that polynomial so it's reduction mod N that is an R mod n, is actually an irreducible polynomial. And this is, y'all remember the last time how I said that the maximum ideals of the integers look like this. P comma F, where P is a prime and F is an irreducible polynomial mod. Right? So you can get that out of this theorem here. So I'm sorry about the screw up on that one direction, proposition 4 through 11. I'll get that on Monday. Any questions? Any questions? All right, y'all have a good weekend and we'll see you on Monday.